And so I would like to argue that this is making the LCA more biological. And so this works. Again, this is just 3 lines of code. Normalize the weights. Get an activation. Cube the activation. So this replaces the threshold. And then this is our Hebbian rule again. And so this has never been published, this Hebbian with the qubit. So again, this learns that the dictionaries, they're almost indistinguishable. Again, you can do the block coding. Now what's exciting about this, here they have like sort of cookie cutter blocks, and you can see the different types of patches get organized together based on what they look like. So again, we have the block coding and the false color. Now what we can do is we can try this with different images from different categories. And so this is taken from color images. And so you can do the same thing. And I think just what you want to take note here is that one, it's moving the colors. It's separating the different regions. And then if you look carefully, you can actually see that there is some sort of continuity to the shapes across the region. And so in a sense, it seems to be clustering things that look like each other. And so, sort of the famous fighting words in philosophers is, the redness of red kind of stuff. And here it's very interesting to see that redness regions sort of emerge, where you have, now if you imagine Sparse coding this again, you could have neurons that fire when this stuff fires, and then that would fire for red things. And not at like a sort of color receptor level, but it's sort of in the cortex level. So here you can kind of see some birds sort of morphing into dogs. You can see, sort of the straight lines over here. You get sort of the cars, like little minivans show up here. And so it's just very interesting to see that sort of categorizes shape. So I didn't tell it, it has no concept of stuff, but just by visual similarity, it's grouping objects. And so this would be very exciting. Like if you use Google Photos now, it can organize all your things. And so this would be the idea, is that you could then organize all the photos of the world, sort of next to each other. And so again, you can kind of see that you get regions that activate the green. So could this be a greenness region, right? So that's open to much debate. So we can do this now for volumetric data. So far we've been looking at pictures and color images and video. But we can also, if we go and take medical data, that's in 3D. And so we can do this for an MRI. It's hard to look at those patches. They just live as columns. But we can take that data and throw it back into an MRI program, and we can get sort of a 3-dimensional dictionary. And so again, this has the block coding on it. So to the best of our knowledge, this has never been published, a 3-dimensional block coding for MRI data. And so now for the last piece, and thank you for bearing with me this far. I know it's been an adventure. I want to talk about compressed sensing. So I can't, for me, people talk about big data and singularity. Yeah. Please, go back.
The X cube, it doesn't have the representational similarity term.
Oh yeah, there's no competition. Yeah, right. So it's actually much simpler. So they don't even fight with each other. They don't have to know about each other. So if we jump back to our where was our, this here? There's this term where they're fighting with each other. This is the competition in the competitive algorithm, and the dictionary has to sort of know about each other. But Elon's saying it's amazingly with the X cubed version, it's much simpler than that. You don't even have to have the neurons talk to each other, right? So now you're saying wires, right? You're talking about wires, like neurons that don't have to connect to each other. And so that's just very exciting that they wouldn't have to know each other. So is that what you're saying? Yeah. Thank you. Let me jump ahead here. So everybody talks about big data, kind of thing. In my opinion, big data was a long time ago. So I have this punch card here. This is one of my favorite things. My old man used to have these in the garage growing up, and they were blank. We just used them to take notes on. I had no idea what they were. It's only later and more recently that I've appreciated, the craziness of these. So just as a quick aside for fun, if I was a true enthusiast and I wanted every possible punch card ever, could I do it? Right? And so this thing has 10 columns going down, and it has 80 numbers going across. So there's 800 little squares. Right? So if I were to have every possible punch card of every possible pattern, that's more than all the sand in the universe. Literally. Right? And so it gets kind of crazy. You realize like the math of these combinations kind of goes crazy for you. But this is an actual punch card. I found this in the second floor. They use these at FAU. right, at some point. But where these came from, and I didn't know this until just a year or so ago, is something called a punched photograph. And so this was an older idea, but it was just sort of discovered by Herman Hollerith, who was the famous one for fixing the census. And what had happened was in the 1880s, the census took like 9 years to count. And they said, well, look, by 1890, we're not going to be able to get it done in time. And so they hired Hollerith to do it, and what he did is he came up with this system. So he borrowed, this is a punch photograph, and it used to be that you got on a train, and the conductor would take a look at you, and then he would punch the hole based on what you look like. Right? So this is to prevent counterfeiting, essentially, and train robbers. So this is essentially compressed sensing. The conductor wasn't making a photograph of you. They were assigning a category directly. Right? And so I think this is sort of reminiscent of how this compressed sensing works, and I just think this is really neat to think that this stuff was here a long time ago. So this was, here's our punch card. This is famously known as Moore's Law. Moore's Law wrote in the 1970s. He wrote a paper about this region here. Later, people said, actually, this has been going on a long time, and now people are starting and saying, actually, this could be a very significant force in the universe. If you continue this curve, you can't go but another few hundred years. If you assume that this is exponential, you cannot go another few hundred years until you hit the light cone, you start hitting cosmological stuff. You run out of sand in the universe kind of thing. Right? So something's going to have to change. We're going to turn that curve around. But for the last 100 years, this is called a double exponential. And so this is a logarithmic scale. Right? So all this is factors of 10. So each one of these are doublings here. So I was watching a talk. Dan knows we like to watch this talk. There's a guy who says this might be the most important graph that's ever graphed. So you think, all right, well, we've got all this data. Can't we just build a nice, new, shiny data center? Won't that fix it? Right? We'll just get lots of tapes. Well, we can't. So in 2007, we passed a point in time where we now exceed the total storage of the planet. Right? Even if you had the budget, there's not enough hard drives on Earth to store all the data we're storing. Worse than that, if you look at transmission, Wi-Fi is getting faster, but not nearly at a rate compared to the fact that your cell phone camera is getting faster. So we're going to have a global overload. Famously, Shannon, he's a pessimist. And so he says you have to take so much data, but we're now finding that's too much data, and that we can use randomness to reduce this. And so amazingly, that if we have a signal that's sparse, we have a signal that has very few non-zeros, then we can multiply this by a random matrix, a set of random numbers. You can think of these as random neuron connections. Then we can get a smaller set of numbers. This is fewer numbers than before. And then amazingly, something that if you go to ask the math department, they'd say you can't do that. But what the whole point of this work is that you can. Candes and Romberg and Tao Donahoe, what they were able to show is that with very high probability, you actually can go backwards. That you haven't lost any information. It seems like you would have. This is not full rank. How could you possibly go backwards? Just take anything out of the null space and add it in, and right, yada yada. But nonetheless, you can go backwards. We'll skip that for now. So amazingly, what we're going to do is we're going to talk about this idea of a single pixel camera. This is a brand new architecture, came out of Rice University. And what they're able to do is you're able to take random projections. You take randomly half the pixels and you add them all up. So this represents the inner product. So you're just going to take a random subset of those and you're going to add them together. And so we're going to take measurements from everywhere and we're going to be able to undo this. So what we do now is if you take on your phone, you're going to take n is in megapixels. You're going to take like 1 million pixels for your smartphone. Your phone's going to throw away almost all that data. It's then going to send it to somebody, and then they're going to do a JPEG reverse to actually see it. The idea is if you're going to throw away all that data, why did you write it down? Why write down 7 million numbers if you're just going to throw them in the trash can? And a lot of times, these 7 million numbers, it's a person in an MRI scanner. Right? It's a person getting x-rays. And so you want to think as fewer numbers as possible is going to be very important. You can save time and money and human life. And so how can we exploit this low dimension? How can we throw away most of our data? So amazingly, what we're going to do is we're just going to randomly sample. So this is sort of the breakthrough, is that you can use random numbers to throw away almost all of your data. And then you can do one of two things. Go back and actually get your data back. Or you can do what brains need to do. You can detect, classify, estimate, and filter. And so I found one paper that talks about compressed sensing in the brain. And so I think there's a sort of tremendous amount of work to explore and argue and say, is this happening? Right. And so for now, for my experiment, what I was able to do is to simulate this digital micromirror device. This is something out of Texas Instruments. This is a little thing. It's about so big. It has 1 to 2 million little mirrors. These little mirrors are the size of a blood cell, about the size of a bacterium. They can turn one of two directions. So these are manufactured the same way Intel manufactures computer chips. They're grown devices. And so what you can do with this is an optical computer. And so this is what you can do is you can set a random pattern onto this mirror. And then that will allow you to sample an arbitrary set of pixels. So this is a digital device. You send in binary, and it will set the position for each of those mirrors. You can update it about 16,000 times a second. These already have a lot of medical application. They already are using this for open surgery. You can do a very interesting spectral camera with this. And so what I was able to do is I was able to use LCA and to recover from this. And so this has never been published. No one has shown that LCA can actually do this. So what we were able to do is to set a random array on here. We take our scene. We throw away half the pixels. The pixels that are left, we just add them all up. And you'd think, well, we've thrown everything away, right? It's like taking all your colors and just mashing them all together into gray. Well, that will, what will that have done? But amazingly, you can go backwards. So here's what this, we didn't build this. This is just an example of what this type of setup would look like at Rice. We simulated this. And then the novel part is using the LCA to do the recovery, which has never been done. And the reason why LCA is exciting is because you can build it in hardware. And so this would be the first time that you'd shown that you can use a hardware-based dynamical system to do this type of recovery. So amazingly, like we promised, we can go past the Nyquist limit. So here would be full samples. And then here we have 50 times sub-Nyquist. And so 50 times fewer measurements than is traditionally required by the signal processing theory. But now we can still resolve that letter R. And so we have to take a number of these measurements, but it's still way less than the number of pixels that we would have had. And so you still take thousands of numbers, but it's much less than the millions of numbers that you could have taken. So if we see what this looks like, what we have here, let me see if I can zoom in on this. We have here a sparse signal. It's hard to resolve here, that the projector's not showing it well, but this is actually 2 spikes. And so we have a signal. Now the traditional theory would say if we want to resolve and actually know where all those peaks are, we're going to have to measure all of our bins. We'd have to take 1,000 samples. And so what we're able to do is make a simulated micromirror. And so this is the random setting of the mirror. So each pixel is either on or off. If it's gold, it's on. If it's blue, it's off. And so we've sort of taken this signal and we've reduced it. And so originally it was 1,000 dimensions, and then we've reduced it to only 100. And so now here's a list of 100 numbers that represents this 1,000 number signal. So then we can able to perfectly recover it. You can see the error is negligible. If we do the minimum energy, if we do like a naive signal processing attempt, we get nothing of meaning. So in general, we have a signal that had 1,000 places where stuff could be. So 1,000 little bins here. But because we knew that most of them were empty, we're able to throw away 900 of those samples, save only 100 samples, and then perfectly recover. We can do this again. The interesting thing about LCA is that you can do this for more than one thing at a time. Because it's matrix multiplication, you can sort of overload it. And here we have 3 signals being compressed at the same time, again with perfect recovery. And then again for 100 signals at the same time. So here's 100 signals all at once. They're 1,000 entries long. We're going to throw them all away to compress them down to 100 elements, and then we're able to go backwards. So just to remind you, we can do this with audio. Here's an audio signal. So this goes like boop, and then this is like, and this is like boop. And so what we've done is we have a signal. Again, we're multiplying it by a random matrix. This time we have a signal that's not actually sparse, right? But it's sparse in this VCT basis. And so the future work will be involved in sort of customizing this dictionary to try to improve these type results. But here we can see that even if the signal itself is not sparse, we can add in a Fourier basis, and then that effectively becomes sparse, and then we can undersample that as well. So here this had 5,000 samples for the signal. We're only saving 2,000, less than half of them, and we're able to get a very nice recovery. So many applications you don't actually need to reconstruct. You can just make an inference. And so we have sort of a hierarchy of detection, classification, estimation, and reconstruction. If I just have to run, right, sometimes I don't need to know that it's a tiger to know that I have to run. So efficient learning, the idea would be, the punchline is, can the brain learn on these compressed measures? Do we have to do the recovery? Right? If I can learn off 2,000 inputs, isn't that much easier than learning off 5,000? And so that would be, the heart of it is that your brain can use random projections, and that provides a sufficient statistic for what it needs to do. So there might be, as Andrew Ng calls it, a common cortical algorithm. You see there was a lot of continuity to these in terms of dictionaries, dynamical systems, sparsity, just x cubed. So hopefully presented some evidence to think that, well, okay, the brain might be doing x cubed, and if it is, then it could probably be doing LCA, it can probably be doing dictionary learning, and it can probably be doing compressed sensing. And so it seems to be this is an extraordinary development in the technological world, and I would imagine we've got a lot of work to do to really tease out, can the brain be taking advantage of this? I'd like to thank my advisors, in particular Dr. Brandholtz. This would have never happened without his incredible patience and support. I'd like to thank George for his wisdom in these efforts. I'd like to thank Howard, especially for his effort